All right. Well, today we are going to finish our discussion of equivalence relations. Okay, so let's review. What is an equivalence relation? Three things.
It's reflective, symmetric, and transitive.
Exactly. RST, reflexive, symmetric, transitive. Yeah? Okay, now, oh, there it is. No wonder you knew it so well. No, I know you knew it anyway. You did that without peeking, right? Anyway. Okay, now, so reflexive, symmetric, and transitive. And last time we did an example, and we constructed this relation rho with these set of ordered pairs. Rho is equal to this set of ordered pairs. And we verified that this was reflexive, symmetric, and transitive, and so therefore this is an equivalence relation, right? And then what we said is we defined 14.34 defines what are called these, what do you call this? This with a square bracket? It's up there too.
Is that an equivalence class?
Yes, this is an equivalence class, right? And these equivalence classes are the sets. So if you have this equivalence class with this one element in it, it's the set of elements from B that are related to 0. Because we have a 0 row 1, a 1 is there, and because we have a 0 row 3, a 3 is there, right?
Could we have the equivalence class of like 0, 2, and that would give us all of the elements? Can you have one?
No. Notice that there's only one element. You can only have one element in the equivalence class bracket. Oh yeah, that's a good point. And so really, and then what we saw is that this equivalence class with 0 in it is equal to this equivalence class with 1 in it. All right? So these are really two different names for the same thing. Namely, there are two different names for this set. And these sets are equal because with sets, order doesn't matter, right? Is everybody with me on that? Okay? And now what I want to do, we did one example last time about a partition. So what do we know about what was the partition here? Do you remember what the partition was?
0, 1, 3, and 2, and 4.
Yes. So what it was is the partition is equivalence class 0 and equivalence class 2. That's the partition. So a partition is a set of sets. And if we were to write this all out, this would be the set of the sets 0, 1, 3, comma, and then the set 2, 4. And what did we say was the characteristic of a partition?
They complete. Or
if you do what to them? If you union, you get the universe. Okay? And if you intersect any pair, you get the empty set. Right? Okay, now the main result that we're going to describe today is Theorem 14.35. Okay, so let's look at this. 14.35 says, let rho be an equivalence relation on B, and let little b and little c be members of B. Okay, so here as an example, here is a row. Okay, and the elements little b and little c are 0, 1, 2, 3, or 4. Right? Okay, so now it says the following three predicates are equivalent. Yeah, watch this. Yeah, so what it's saying is that A is equivalent to B, and A is equivalent to C, and B is equivalent to C. It's saying that these three, each one of these three, the following three predicates are equivalent. So what it says is that if B row C, that's equivalent to B equivalence class B intersection equivalence class C is not equal to the empty set. And it's saying that B row C is equivalent to equivalence class B equals equivalence class C. And it's also saying that equivalence class B intersection equivalence class C is not equal to the empty set, is equivalent to equivalence class B equals equivalence class C. I mean, all that English, right? But I think before we talk about this, I want to show you, let's do with this example, let's do this with this example. So here's 14.35, just this is not a proof, this is an example. 14.35 example. So check this out, you guys. Let's use first of all let's use 1 and 3. All right? Because 1 is an element of B and 3 is an element of B, right? So what does A say? A says what? 1 row 3. Now I ask you, sports fans, is this true or false? In this example, is this true or false? Testing, 1, 2, 3. Is this mic working? Testing. Yeah, it is true. Why is it true? Because they're related. Because there's ordered pair 1, 3. Yeah. 1 row 3, right? The alternate notation, right? Remember the alternative notation, yeah?
1, 3 is an element of row. Okay.
Well, yes, yes. So does everybody agree that this is true? Right? So this is true. Okay. Now let's take a look at B. What does B say? It says equivalence class 1 intersection equivalence class 3 is not equal to the empty set.
Sure.
Well, look at equivalence class 1 and look at equivalence class 3. The intersection is not equal to the empty set. Is that true or false?
True.
That's true. Are you with me? True. And what about this? Equivalence class B equals, so equivalence class 1 equals equivalence class 3. True. True or false? True. That's true. Where's my...
True. Super true.
Okay. On the other hand, let's take a look at, let's do 1 and 2. What is 1 row 2?
False.
That's false. Are you with me? So false. And what about equivalence class 1 intersection equivalence class 2 is not equal to the empty set? True or false?
False.
That's false. And what about equivalence class 1 equals equivalence class 2? That's false. Are you with me? So these 3 predicates, it says the following 3 predicates are equal. Each one of these predicates is either true or false. Yeah? Okay? So if one of these is true, they're equivalent. If one is true, they're all true. If one is false, they're all false. They're equivalent. They are equivalent. All right? Now, what we're going to do now is we're going to prove this. We're not going to prove it now. What we're going to do is we're going to give an outline of a proof, and you're going to help me prove it in the homework. Okay? Now, here is how we're going to do this. This is actually a very clever, a very clever argument. It's a little bit different from the way we've. I mean, one way we could do this is we could do equivales. We could do we could prove A equivales B, and then we could prove B equivales C, and we could prove A equivales C. We could do that. Okay. But instead of doing that, here's the way we're going to do it. So 14.35. This is not an example. This is going to be a proof. 14.35 proof. Now look, you guys. This has 3 parts to it, right? Here's what and it has an A, B, and a C, right? Here's what we're going to do. Now check this out. This is pretty clever. Here's what we're going to do. We are going to prove, the proof is in 3 parts. The proof is in 3 parts. Okay, so here we go. What we're going to do is we're going to prove part A, not equivalence. We're going to do part A implies B. That's going to be the first step. And notice it's not equivalence, it's implies. Then what are we going to do? We're going to do part B implies part C. Are you with me? And then we're going to do part C, exactly right, implies part A. Okay, and
that's easier than doing all equivalent?
Yes, and this is much easier than doing equivalence.
Are we assuming the context?
Well, let's think about how. Well. Okay. Now, how we do each one of these? So you understand, we're breaking this into 3 parts. Now, each one of these 3 parts is a big proof. And what's going to happen is, I'm going to prove. In class, we're going to prove. Let me see which one we're going to do. We're going to do this one. A implies B in class. But you're going to do, for homework, you're going to do B implies C, and you're also going to do C implies A. But wait a minute. Why does this? But before we do all that stuff. Why does this?
We're proving that they imply each other, not that they're equivalent.
Yeah. So wait a minute. Yeah. What's going on here? What do we? Why? If we do this, how come this? Why does this prove that they are equivalent?
Transitivity.
Yeah. There's something about transitivity. So why is this a proof of equivalence?
Because if they're all equivalent, then okay. For example, if A implies C and C implies A, then that means
if they imply each other, they're equivalent.
There's a mutual. Very good, mutual implication. Okay, so actually this is based on, and not only that, but it's based on transitivity, right?
Well, because the A is not directly.
Yeah. Okay. So there's actually two reasons. Okay.
Mutual implication, transitivity.
Yeah. Okay. So we can erase this example now. Okay, so there's 2 reasons why this is a proof that they're all equivalent. Okay, so first of all, it's based on transitivity and mutual implication. Okay, so what happens is if we have B implies C, this is part B. If we have B implies C, and then we have C implies A, then by transitivity, what will we have? B implies A. So by transitivity, okay, so now that, so by transitivity, if we just do these 3, we know that each one implies each other one. But now, if we know that each one implies each other one, okay, so by mutual implication, what we have is if we have A implies B and B, this part A implies part B, and part B implies part A, okay, what does that equivalent?
Part A equivalents
Part B, yes. This equivalents A equivalents B. And you can do similarly for each other pair, right? And similarly for the other 2 pairs. And similarly for the other 2 pairs. So by doing that, we will have it. So now does everybody understand this? Okay, we're all set. So now's all we have to do. Okay, now we're dividing and conquering now. Okay, now there is on the web page, for those of you who don't have access to this right now in class, I have hints for how to do 14.33 B implies C, and 14.35 B implies C, and 14.35 C implies A. It's exercise 14.34. So I'll hand these out. And there's quite a few little details there, but I'll let you read that. And that's going to be due. Now remember, I'm away at a conference on Thursday, so this class doesn't meet on Thursday, but this is due on Monday.
Is that just you?
It's just me. Wait a minute, did we have an assignment? No, I'm sorry, there is an assignment due.
Yeah.
There is an assignment due Thursday while I'm away. You can put it in the box by my office. But this one is a Monday. This one is a Monday assignment. All right, so now just to give you an idea, to show you, how this works, what we will do now is we will prove part A implies part B. So this is a 14.35 proof that part A implies part B. Okay? So let's write out what it is that we're proving. We are trying to prove what? B row C implies what? Equivalence class B intersection equivalence class C does not equal the empty set. All right? Now, what we're going to do here is we are going to, we're not going to use our favorite technique. Our favorite technique is what? Assume the antecedent, then start with this and get it to true. Well, in this particular case, it's easier for us to start with the left-hand side and get it to imply the right-hand side. Okay, so what we'll start with the left-hand side, equals, implies, equals, implies, equals, and then to the right-hand side. So a sequence of equals and implies, starting with the left-hand side and ending with the right-hand side. Are you with me?
Yes.
Good. Okay, so here we go. B, oh, and by the way, what will we always use? What do we know about row? What kind of a relation is row? With all of this discussion, what kind of a relation is row? Well, it is a binary infix operator, that's true. But what kind of a relation is it? It's an equivalence relation. So, and what are the three attributes of an equivalence relation? Reflexive, symmetric, and transitive. So we can use those anytime we need that, we can invoke that because this whole thing. Are you with me on this? Okay. So B row C. Now, so B row C. Okay, now I'm sorry about this. I apologize profusely. But this equals by, I'm going to pull a big rabbit out of a hat. Okay? And here's identity. No. Identity of and, which is 3.39. Yeah, I told you. I knew you'd choke on this.
You're just going to go.
I'm just going to, yes. We're going to put it on the left-hand side. We're going to do this. This is true and B row C.
Wow.
Okay? Now, watch this. Watch this.
There's a better way.
No. Row is reflexive, right? It's an equivalence relation, right? So this equals by the fact that row is reflexive. Now what does reflexive mean? Because it's an equivalence relation, it's symmetric, it's Ristel, reflexive, symmetric, transitive.
It equals itself.
That means that any element is related to itself. Okay, so what do you think we should do? Look, you can actually, well, what are we trying to get this? We're trying to get this to something like this, right? B row C.
We want true and B row C and B row.
Well, what? No. What about true? I'm saying row is reflexive. So what can we put here in place of true because row is reflexive?
B row B.
Yes. Yeah. Did you guys hear that?
Okay.
You see? So we can do B, row, B, and B, row, C. Because we know that B, row, B is true because row is reflexive. Are you with me? Okay, now, with that, okay, now look, what do we have to get? What shape of things do we have to get over here? We have to get some what?
Brackets.
Some brackets. But we don't have any brackets here. How are we going to introduce the brackets? How are we going to introduce the brackets?
X row B equals X is an element of bracket.
Yeah, for 1434. Here we have an X row B, but that's the same thing as saying X is an element of... Are you with me?
Yeah.
So that's the relationship between the what it means to be an equivalence class, right? If B is an element of that equivalent, yeah? Okay, so how do we, so this equals by, this is so cool. 14.34. What? So B row B means what? Element. Yeah, so this is B is an element of equivalence class B. And what?
You want on the other side? Which
Hmm?
one do we want?
Both of them.
We want bracket C. Right?
Yeah, so B is an element of
Equivalence class B, and
B is an element of
B is an element of equivalence class C. But now what are these equivalence classes? They are sets, right? And what do we have here? But what do we have here?
intersection. We use the
No, what is it? Yeah. Huh?
38. 48.
25, the meta theorem?
No, not the meta theorem. You're close though. You're getting warm. You're warm. You're hot. You're hot.
12 like
Oh, intersection.
Intersection. 11 point what?
21.
And what does 11.21 say?
B is an element of S and B is an element of T.
T
Equals
B is an element
of S intersection.
of the intersection. And then we'll have the intersection of B and C. And here, this is we have got the intersection of B and C.
So B by 1121, B is an element of.
Yes. So equals by, very good, 11.21.
B is an element
B is an element
of
of what?
equivalence
The
class B intersect.
B intersection
Equivalence class C.
equivalence class C. Isn't this stuff cool? I just think it's neat how we have all this machinery that we've learned and that we can apply to this new thing. Okay? And now what? But now what do we have to get? Now what?
we need to get rid of the B and get an equal.
And get a not equal to the empty set. Now just think a minute before we formalize this. Is this, if B is an element of something, what does that tell you about that something?
In both of them.
No. If B is an element of a set, what does that tell you about that set?
Set is not empty.
It's the set can't be empty if B is an element of it.
Right.
Now,
Oh, that's cheating.
no, we're not going to cheat. Here's what we're going to do. We're going to make it a lemma. So this implies, so if B is an element of this, that implies that this is not equal to the empty set. I claim that. Okay, so, but we need to prove it. Okay, so this implies, and we're going to make this a lemma. And our lemma is going to be this. Our lemma is going to be B is an element of, we'll just call it big A,
Implies that A.
implies that A is not equal to the empty set. Okay, that's our lemma. And if we accept it, and we will prove this lemma, but if we accept this, and well, you can tell that it's true, but if we accept this, then this implies what?
What we want it to be.
Yeah. B
Intersect.
intersection C
Not empty.
is not equal to the empty set, right? And that proves that, but we need to prove the lemma.
I don't like this.
What do you mean? This is a lemma? I think this is cool.
Rabbits. And
Rabbits, well, you're right. Yeah.
rabbits. And
Rabbits, but anyway. I think this is the cleanest way I think we can do this. Okay, so now let's prove the lemma. Okay, so So the lemma is this. We want to prove B is an element of A implies A is not equal to the empty set. And guess what we're going to do here? Another proof technique. Oh, this is such great proof techniques we're using. Yes, contrapositive. We're going to do proof by contrapositive. All these great techniques. And so what will we prove? Let's write down the contrapositive.
A is the empty set.
A. Yeah, it's
By double negation.
by double, yes. So it's not this implies not this. Yeah, it's not the consequent implies not the antecedent, right? Okay, so but not this is A equals the empty set implies what? But now implies what?
B is not an element.
Yeah, not B is an element of A. Are you with me? Oh, this is so good. Okay. And now how will we prove this? Yeah, we'll prove this by assuming another proof technique. So we will prove by assuming the antecedent. Prove by assuming antecedent.
Are we going to lemma our lemma?
And sometimes that does happen. You have a lemma in a lemma. So we will just, what we'll do is we'll start with this and we'll get it to true. All right? We'll start with the antecedent. Sorry, we'll start with the consequent and we'll get it to true. So it's not B is an element of A.
Equals for equals.
Equals, equals by assumption. Our assumption, what is that? A equals the empty set, what? Not B is an element of the empty set. But this equals, don't we have something about B being an element of the empty set?
It's false.
Is that do you have a number for that? I think that's a property of the empty set, yeah? What is that? Can someone look that up? You guys out there in video land, look this up. Tell us. 11.42 or 4.2? Okay, so it's
E is an element of the set.
empty set equals false. Okay, so this is 11.4.2. Okay, so this is not.
Not false.
Oh yeah, so it's not false. Huh. Oh well. Not false equals by what?
3.8.
8. No, 3.13.
3.13?
Is that the better one?
I think it's directly. Don't we have a not false equals true?
Yeah, 3.13.
Okay, true.
3.8 is not true as well.
Boom. Yeah? Now, is that cool?
Pretty cool.
I think that's neat. All right. And so now you have these, you've got these hints. And, talk about a lemma of a lemma. I mean, this is divide and conquer.
Yeah.
And don't try to do this. And I've had students try to do this a different way. And every time they try to do it a different way, there's an error in it. So I advise you, I put the really detailed hints here to guide you in the proof. And this is something that you need to know. If you have to prove this on the next exam, the hints won't be there. Okay, so fair warning right now. Okay, so anyway. All right. Now, so that's one big result. Now, the second big result that we want to look at with equivalence relations is this idea of a partition. So we will close today with this concept of a partition being the same as an equivalence relation and an equivalence relation being the same as a partition. So let's take a look at 14.35.1. 14.35.1 says, let rho be an equivalence relation on B. The equivalence class is partition B. Actually, we should probably review. Let's bring this up, actually.
Partition set S partitions T if the sets in S are pairwise disjoint, and the union of the sets in S is T.
Yes. That is 11 point what?
76.
Here, I think we should look at that. Here. This is an axiom, so it's just a definition of what a partition means. So set S partitions T if the sets are pairwise disjoint and if the union of the sets in S is T. And then I think I remember looking at this complicated expression one time.
Set of sets?
Yes, that is true. S, oh, I erased it. Remember we had the example of the set of sets. 1, 2, 3. Remember over here on this board? Remember we had like, I think it was 0, 1, and 3. And the 2, I think it was 0, 1, 3, and then 2, 4. So this whole thing is called a partition. And an element, because it's a set of sets, and each pair of these sets is disjoint.
0, 1,
and
2, 3, 4.
and 0 is, yeah. All right? Okay, so the sets, so this is what it means to partition. So sets in S are pairwise disjoint, and the union of the sets is T. So if we're going to prove, so now let's go back to here. To 14.35.1. If we're going to prove 14.35.1, then what we need to do is we need to prove both those properties for the equivalence classes. Okay. So let's do an example of 14.35.1. So for example, if this is T, suppose T is this set. We've been using numbers. Let's use letters just to be different. A, B, C, D, E, F. Let's stop at F. You talked me into, okay. And then S would be this. A, C, E, B, F, and D. The set D. So this is what it means. This is what it means to be a partition. And what we are claiming is that if rho is an equivalence relation, then the equivalence class is partition B. All right.
Okay. So
14.35.1 proof. Yeah, they are these. You know, the equivalence classes are defined by 14.34. That's what the equivalence classes are. So 14.35.1 says what it does is equivalence relation, and then that gives us a partition. Okay? And so the proof is this. So first of all, we say let rho be an equivalence relation on B. Now we're going to say B. And we must prove both properties of partition. Must prove both properties of partition. Okay? And the first property is, and those two properties are 1, pairwise disjoint. And 2, union is B. Are you with me? Now, I'm sorry, you're not going to like this because this is going to be a little informal. But, so let's do proof of 1. Now, so what must we prove? We must prove, in order for them to be pairwise disjoint, what must we prove? We must prove that, so here, must prove that equivalence class D does not equal equivalence class E. Now what I'm saying is that these are different equivalence classes. Okay, so they're not equal. I mean, obviously if they're equal and it doesn't apply. But if they're not equal, then that means that they are different equivalence classes. So what must that imply? If this equivalence class is not equal to this equivalence class, what must that imply? That what?
The union of them is not the intersection?
Yes. No, not the union. The intersection. This must imply that D intersection E is not equal to the empty set. Oops.
Which is the same as a lot of things.
Yeah, actually, actually, look, does this look familiar?
Yeah,
It's
D row E.
D. But what is the contrapositive of this?
It's our lemma.
It's not. It's not our lemma. It's our. It is. Yeah, that's what it is. Here.
It's right there.
Yeah.
It's something like that.
Yeah. Okay. We must read. But this looks familiar. But the contrapositive of this.
There it is.
Yeah.
It is something we're going to prove for homework.
Yeah. Yeah. But the contrapositive of this is what? Is D intersection E
Is the empty set.
equals the empty set implies what? D equals E. And this will be proved in the homework, right?
No.
Or not? Is this the one we did?
We still need a not equal somewhere. In the homework we're proving not equals the empty set implies D equals E.
Did I write this down wrong?
That's the must prove. Look at compare with this.
Oh, this isn't right.
That's the equal.
This, yeah,
Okay, that's better.
yeah, duh.
Not the same, then the intersection.
Is if they're not the same, then the intersection equals the empty set. I was mistaken here.
Right.
Okay, it equals, and then the contrapositive of this is this implies this. Okay,
Now we're good.
now we're good. Okay, but this is proved as part of the home. Actually, is this the homework one or the one we did?
That's the homework.
Okay, this is homework.
B implies C.
Okay, so assuming that you do the homework, we've done that one, and now what? Now this next one you're really not going to like. Proof of 2. I predict there will be howls of protest. Okay, and so proof of 2, and we're going to do this informally. That that the union is B. Okay, and this is going to be an informal proof. Now you're going to have to imagine this. Okay. Now, do you agree that every element of big B is in at least one equivalence class?
Yeah.
Every element
Except we're using T and N.
of big B, well, I mean here, the one that we're proving is, well, I guess over here we said let rho be an equivalence,
Right.
be an equivalence. What is this? Be an equivalence B? What is? That doesn't quite make a little.
I guess this isn't related to our example.
Be an equivalence relation on B. Sorry, I left out some words here. Be an equivalence relation on B. Let rho be an equivalence relation on B.
Oh, right.
Okay? And now what we're saying is every element of B is in at least one equivalence class. Every element of B, we'll give it a name. Say X is in at least one equivalence class. Namely, what equivalence class is it in?
Isn't the union T? I don't know where we got B from. I'm just confused.
Well, I'm sorry, because this was using T and S from the definition of what it meant to be a partition. So I switched.
Oh, so we just used it.
Yeah, sorry. Yeah.
But it is T, essentially.
Yeah. Okay, so okay, tell me, what equivalence class is X in?
I don't know. X's.
Yes. X is obviously in that one because X is related to itself, right? Because rho is reflexive. Are you with me? So doesn't that tell you that the union of all the equivalence classes is B? Boom. End of proof. End of informal proof. Do we want to have slashes for informal proof? Or maybe this and it's not quite a formal proof. A vague proof, whatever. Okay. All right, so that's 14.35.1. Now look at 14.36. 14.36 is going the other way. All right. So 14.35 says given an equivalence relation, prove that the equivalence class is partition B. 14.36 goes the other way. Given a partition, it defines this B rho C is defined as the relation based on that partition, and the claim is that rho is an equivalence relation. Okay, so 14.36 goes from a partition to an equivalence relation. Okay, and now you got to be careful here. This is a little tricky to read this, but notice that here we have a little p. Now little p is not little rho. Okay, so look, so rho is an equivalence is a relation. Rho is a relation.
Bad choice of variable.
Yeah, but that's the way the book is. And then P is a set. It's not a set of ordered pairs. It's a set of elements in B. Are you with me? P, little p is a set. It's a set of elements in B. Like if we had this here, P, look. But what we're saying here, let's do an example. Let's do B equals A, B, C, D, and then our partition. Let's say that the partition is the set S, and that would be the set. Let's make it be A, C, D, and B. Are you with me? Then P is one of these sets. All right? You see, so P. So what does it mean? So what is this B rho? So what is this B rho C? What about like AD? Suppose with this example, what is it? A rho D. Is that true or false? Is A rho D true or false?
True.
Why is that? That because at equivals there what? There exists this, there exists a P, all right, a set, in range P is in, this is P. We call this a partition. Use their number. Capital P, all right. P is in this partition. Are you with me? P is an element of this big P, and body what? Here,
A is an element of little p.
A is an element of little p.
Which is true. And D is an element.
And D is an element of little p.
That's true.
And this is true. This
Whole thing.
Yeah. So we have A rho D equivals true. Right. So that's an example. All right. Now to do this. So that's the definition, this is the definition of this rho, and what would we have to do to prove that this is true? That it's an equivalence relation? If you can just tell me this, even if we don't finish, which we're not going to finish, but Can you tell me what we'd have to do to prove that? What are we trying to prove? To prove 1436?
We have to prove that it's reflexive.
Ha! Very good. To prove 14.36, must prove that rho defined by this, is reflexive, transitive, or symmetric, RST. Reflexive,
In that order.
well, it doesn't matter. Transitive, right? We'd have to, so it's in 3 parts, right?
Yeah.
So 1, reflexive.
B or B.
We have to prove that B rho B. So B rho B, okay? So this equals, by definition of rho, what? The definition's right there.
The quantification.
Yeah, there exists a what?
A B.
No. A little p. There exists a p.
P is an element of
P is an element of the partition, right?
partition.
And what?
B
B
is
is
an
an element of P and B is an element of P.
B is an element of
Little p.
B. No, B rho B, right?
That's not what it says.
Oh, sorry.
B is an element of P and B is an element of P.
Yes. B is an element of P and B is an element of P. Okay? But what is this?
That's true.
No. What is it?
B is an
That right
element of
there
P.
is.
What do we know about
Idempotent.
idempotency? Idempotent and, right?
Yeah.
So this is, there exists a P, what?
P is an element of P.
P is an element of P.
B is an element of
B is an element of little p. Okay? But each, I'm sorry, this is going to be, what do you call it? Little informal. What do we know about this? B has to be, what do we know? Each element has to be in one of the sets, right? So, little informal here. Each element must be
Given a partition.
in one of the sets. Right. Actually, it's because the union because of that union. And so this is true. Okay, now let me tell you that I'm not going to bother to do part 2 and part 3 is actually given in the book, and we don't have time to go over it. I don't think it's important that we do those details. So this concludes our discussion of equivalence classes, and I won't be here again, to remind you, I won't be here on Thursday, but on Monday we'll start functions.